for joining us today. I'm going to go ahead and pass it off to Jonathan to get started.
Hi, my name is John. Thank you for being here today. I'm just trying to grab access. A few housekeeping items. We're going to have the attendees muted during this session. If you have any Zoom issues, please contact us through the chat. We do have 10 minutes slotted for question and answers at the end. Feel free to send your questions in at any time, and I'll try to respond throughout the session. And also, of course, the webinar and slides will be available after this presentation, so you'll have everything that we've talked about. And my hope is actually during this webinar, you can follow along, and if not, you always have the webinar itself and the slides. So with that, thank you for being here. My name again is John Herkey. I'm a developer technology evangelist at TigerGraph. My background is a computer networking engineer in the Army. I did that for 8 years. I'd go out in the middle of nowhere, I'd shoot up to a satellite, grab an uplink, and deploy a network. So you imagine just a barren field of nothing, and then all of a sudden you have a whole base and soldiers and Black Hawk helicopters flying in and computers and all that infrastructure that goes along with that. That's what I did. I programmed routers and switches and created those networks. I did that for 8 years. And then I also, at the same time, joined a company called United Health Group and did that in the data centers for 1.5 years until it got a little bit repetitive. And so I ended up switching and did a 180 and went in from technical into the business world. And I was an entrepreneur in residence building healthcare startups for about 2 years. And then in August 2016, we decided to break off inside this internal group here that was the startup incubator in this healthcare company. And we decided to look at emerging technologies because we noticed that there was this trend of all of these emerging technologies, but people didn't understand how to harness them. I think the greatest one is if you've watched the old TV replays, people are like, what is the internet? What's a web page? Do I need a web page? Is the internet going to be around? And of course, today that just seems really, wow. They don't know what the internet is. They don't know what a web page is. They don't know what it's used for or how we could derive value out of it. It just seems so like, wow, that's illogical. Like it should be logical, like that there's value in it. But that's the same trend that we're seeing with these emerging technologies. So in today's world, we focused on graph databases and focused on AI, which is a laundry list of different things: natural language processing, machine learning, deep learning. There's so many things in the AI field, blockchain technologies, Internet of Things technologies. So I did that for a few years until late 2019. After building a graph community inside Optum, I got a job offer at TigerGraph to become the technology developer evangelist, which is a fancy word for just being able to help others learn about the technology and help them get started. At the same time that I worked at this company called Optum, I founded a company called Future Scammy, which was focused on bringing emerging technologies to schools. There's a huge gap in education with these emerging technologies because they come out so fast that the teachers aren't able to apply these emerging technologies in school. So that's a little bit about me. And then a little bit about TigerGraph for those that are new. TigerGraph really focuses on helping customers improve their insights on their data. Some of the customers that are listed there: Intuit, Zillow, Open Corporates. It was founded in 2012 in Redwood City. A little bit about why graphs and why now. As I talked about where I used to work, we did all of these things, but what starts to happen is there's a convergence of these technologies and a convergence of data. There's so much data out there, and the data is getting more diverse, and there's more connections and correlations between data than ever before. And we can't always keep our data in silos. We need to be able to have sort of this mesh network of value that we can derive these insights in real time. We have to be able to connect open domain knowledge to corporate knowledge and deliver those results in the same speed that you could write a Google search. So Just imagine having your data unlocked and be able to access your data in the same amount of time it takes you to type your search string in Google. We're going to dive a little bit deeper into the AI machine learning. I get this question a lot. Where's the intersection between AI and machine learning, and how does it fit within graph? There's a couple answers to that. We're going to address one of them, which is actually data enrichment and storing that enriched data in the graph, so we can actually create more insights and connections between our different vertices and create different interesting data value points, I guess you could say, or data insights that you wouldn't have had before because you didn't have that data pre-processed. And we'll look a little bit into that. If you're not familiar with graph or what graph is or what it would look like, to the left-hand side is a graph representation. You could think of this as you could think of this as sort of you have vertices are sort of like entities, and your entities then have a relationship to other entities. So this one talks about customers placing an order and then shipping. So they have like a location. And so that order has relationships to the location and customer and payments. Where this gets really useful to have your data modeled in representations is when you get to use cases like fraud and supply chain optimization. So in fraud, you have these fraudsters that are legitimately trying to deceive everybody else. And so they have this really complex methodology of transferring money between this source and that source and this source, and they're trying to, they know that your data is in these silos, and that there's no way that you can track them across all these different systems, across all these different places. But then you introduce graph, and you can instantly see their fraudulent activity by tracing deeper and deeper and deeper, and you can follow the money and find where those fraudsters are actually at, and you can represent those as patterns. And so things that you can't do traditionally with relational databases, you can in the graph database world. A little bit about graphs. I took this off a blog from Google because I love it, and I think this is one thing that really sparked graphs and the label property graphs of the world. And this is Google saying things, not strings. And so what they're basically saying is that instead of just having relational, why don't we store the relationships between the different entities, and then we can derive those entities and get richer, deeper insights on our data. So if you've ever used Google, you're using graph. If you used LinkedIn, you're using graph. If you used any social network, you're probably using graph. If you use any kind of recommendation system or Amazon product recommendation, you probably have touched graph. If you are in the healthcare space and you're trying to recommend drugs, you can use graph. So instead of recommending products or recommending ads or recommending movies, why don't we look at the correlations and patterns between individuals and recommend them the best maybe procedure or drugs. So a little bit about the use cases. We showed the lines and dots. That doesn't mean that your end output is lines and dots. Not always the case. There are cases where it is pretty interesting to see the connections between the elements, but I would say most of the time you see something like this. So this is a member journey, and this is a patient named Doris. And Doris interacted with the healthcare domain many times throughout her life. And what you're seeing here is all these different events that Doris interacted with the healthcare. But what's really powerful is that this information was retrieved in 50 milliseconds. So imagine 50 million patients and connecting all of the dots between all of the different data elements and bringing that back into a single view of your patient and being able to do that in real time. It's sort of the first time you see that or hear about that, many people's reactions that's not possible. It's impossible. You could never do that. It is possible. I've done it. So, and if you are really curious about how to do that, we do have a synthetic data set that I can actually generate, and you can experience this as well. Excuse me. The other interesting use case is, I really like this one, even though I have no relevancy in my background to phones, but I think what it illustrates is really good. It has on the left-hand side a good phone and on the right-hand side a bad phone. Why this is important for my background in the healthcare space was because we needed something that was explainable. We couldn't just always put everything through a black box and do machine learning and, oh, it just magically picked out this prediction. Great, how did it magically pick that out? We needed explainable AI. And I think that's where the illustration of this good phone versus bad phone really shines. And that we have on the left-hand side, you have sort of these patterns or correlations between what is a good phone. And a good phone has a stable group. It has many connections. It has the ability to, it looks like callbacks. So on the left-hand side, you see number of calls between phones. You could see that there's relationships between phones, so a friends network. So that all illustrates a good phone. On the right-hand side, you have the person that you've probably got those spam calls, and or trying to sell you something or make you click on a link or whatever. That's the pattern of a bad phone. And so you can create these patterns and then look at the patterns of the data, and you can derive whether it's a good or bad. And you can do this in real time. So you can actually like block that phone from actually being able to contact your customer if you want. And this is just cell phones, but imagine all the other domains that same pattern can actually be applied to. This one, because we're talking about COVID-19, I created this actually from real data, and this is the South Korean Center of Disease Control and Prevention data. So they're able to extract all of this data and then put it together in these CSV files. And then what I did was I took the CSV files and I said, okay, on the right-hand side, I can see that they've actually marked patients and patients, but it's really hard to see patients infecting patients, infecting patients, infecting patients. So, you know, one thing I wanted to see was these infection chains. And the other thing I wanted to see was, is there any event that occurred that even though that this person wasn't marked infected by, could have been possibly infected by this other patient, even though that they weren't reported that. And the cool thing about this data source was it had the timestamp along with the latitude and longitude. So what we can create there is a time event when somebody was at the same place and at the same time as somebody else. And so by doing that, we could then find correlations of unknown infection chains, possible infection chains. We don't truly know if that person infected that person, but they were at the same place at the same time within 3 feet, 5 times different events. So there might be some high correlations. And hey, there was a bunch of people that were at this place and they all got infected, but I wonder if somebody there brought the infection and then passed it on. What's really awesome and what's really neat about doing this is that we can run these insights and these analytics in the database itself. So you don't have to transfer all of the data out of your database and then run something on it and then transfer it all in. You can run that in real time. One of the queries that I have for this specific workshop is Similarity. And so one thing we want to do is when we get into looking at these COVID-19 papers is we want to find similar papers. So if I'm a doctor, I want to find a similar paper to this one, that would be a really good use case for a similarity algorithm. All right, so a little bit about the challenge and why everybody's here today. Well, I guess everybody's here probably to see the pattern of how this works, but what this project was actually on was the White House opened a challenge and saying that, hey, we have 68,000 full text articles about COVID-19. We have 135 scholarly articles, and there's just so much data, and there's so many publications coming out that we can't keep up. We can't, as a doctor, I can't actually understand and see everything that's going on. I don't know what the publications I should be reading. There's just so much noise. And so the White House issued a challenge for everybody in the KO community to build a solution that helps doctors be able to answer questions that they might have on those papers. So if I wanted to ask a question like, what's the most relevant paper for COVID-19 that deals with cancer or something like that, we could answer that. We can answer that in real time. So what we want to do is we have this, and this is all text documents. And what we want to do is be able to semantically link that. So basically what we're doing here is doing exactly what Google did. So you can have a claim to fame that I could replicate Google, or I could build Google after this. You'll be able to semantically link your artifacts as well. That's all Google's doing, is they're pulling in the web pages, which are text. You've probably heard of a thing called SEO, which is search engine optimization, and you're putting keywords and terms, and Google is going in there and scraping that data and then joining that data and then making that data accessible for you to write your searches on. We're going to be doing the same thing. So one of the tools that we're going to be looking at today is called SciSpacy. And we're going to look at a flavor of SciSpacy called SciSpacy. So SciSpacy is for biomedical text processing. And what this allows us to do is look at biomedical text and be able to articulate the entities that are in that text. So on the right-hand side, you see regular SciSpacy. You see some of these things like Peter Strock. That's a person. So they have all these people, and that's an entity for a person. That's person class. So what we're going to do is actually look at biomedical language and text. And for that, we need specific models that are trained to understand biomedical literature. So in the middle here, you can actually see some of these models that we're actually going to run. I've done because it does take some time, and we're using a free Google Colab notebook. I've pre-processed it for the sake of time, but you'll be able to do this on your own and replicate it and process it and use your own data that you extracted. All right. So this is the full end-to-end pattern that we're going to be doing here. We have the documents of data on the left-hand side. One thing that they included was a metadata file. The metadata file is really neat because it's got the author, it's got a publisher, it's got the URL for the actual document. It has an abstract of what the paper's about, and then it has a date when it was published. And that's enough information to really give us sort of an ABCs of this semantically linking and running NLP. So we're not processing the 12 gigs of documents. What we'll be doing is taking that metadata file and processing that, and then representing that in graph. So we have the data, which is text, run NLP on it, which is doing enriching. So we're running a machine learning model, doing natural language processing, which is doing entity extraction. And then we're doing semantically linking it. So we'll create a graph that can actually handle and understand the data that we're passing it. And then we'll run some insights into it. So we'll run some algorithms or queries, which are basically, if you think about asking, it's a little weird to think about talking to your database, but think of like, I wonder if I could derive this insight of ask the data this question. Okay, how would I write a query to ask that question? And then you can get the answer for that. So that's the pattern we're going to do. I did want to mention Akash. Akash is a rising senior and a pre-med student. He's the one who spent the time the last 3 weeks putting this workshop together. He also has some blogs out that will run you through step by step everything we talked about. So those will be included. And you can use those as reference materials, or you can use this video and just follow along. All right. So we're going to get into the workshop. So this is a workshop. I'm not going to just be talking the whole time. And we're going to do this live. And the links, if you're following along and you're on YouTube, the links will be in the description. If you're following along and want to participate in the workshop live while we're talking right now, the link will be in the chat. So the first link I'm going to give you is this one. All right, all panelists and attendees. So this will have the data that we are going to be looking at. It will also have the pre-made model that we're going to be using. They have an import and export feature that is very handy for these type of things where we want to spin up a demo. So the next step, once you have, I would just click on that link, click on the link on YouTube or click on the link in chat, download the data. And then the next thing we want to do is go to TG Cloud. All right. I'm going to open an incognito so I can see what you see. All right, so you'll land on a page like this. If you have a TG Cloud instance, you'll just want to log in. If you don't, you'll want to sign up. And once you sign up, you'll end up in a portal like this. All right, except yours won't probably have a lot of stuff in it. That's totally fine. So you'll end up on your dashboard page. Your dashboard will look really blank if this is your first time here, so you won't have any of the graphs or the activities, but that's totally fine. Just to give you a little bit, you have your account up here. If you have support, if you have some issues, you can always click on support. If you have questions, you can use the FAQ. And then where we'll go after this, hopefully everybody's following along. If not, feel free to watch the video afterwards and reference the materials. So the next part is go to My Solutions. And what you want to do is hit Create Solution. Now, the Create Solution, we do have some kits that are available. I talked about the COVID-19 CDC prevention. The kit for that is actually right here. So if you want to have that full demo with the queries and the data and everything modeled and want to play around and discover new patterns or add things to it, all you do is you can click on this and then click Next. For ours, I'm just going to choose blank, but there are many other kits. So if you're interested in healthcare or fraud or recommendation engines, feel free to sort of navigate this starter kits and choose one and play with it. You can always spin it down and then spin up another one. I'm just going to choose the blank. Okay, so next we want to choose a platform. We have AWS. If you are going to use if you want this for a production or for your real POC, and you don't want the instance to shut down every hour, when you're using this, it won't shut down, but if you're inactive for an hour, it will shut down using the TG free. So if you don't want it to shut down, choose this option. If you don't mind it and you're just doing a POC, TG free is the way to go. Choose the location that's next to you. Disk size is 50. Of course, if you do a paid one, you can choose different ones. All right, and don't all name it the same as I name it. It'll error out. But choose a unique name for your solution and for your subdomains. So we're going to do NLP COVID-19. I'll do JH. Change. Suppose I could just copy and paste. And then don't forget your password. If you forget your password, you might have to terminate and bring it back up because you're the only one with that password. And I'm just going to paste there. All right, and then once you're done, just check everything looks good, hit submit. All right, so this will spin up. It says grab a cup of coffee. It does take a few minutes, but what we're gonna do is actually switch over to the NLP. And I'll get to the chat here once we get some time to give feedback. All right, so the next thing we're going to do is jump over to this. Actually, I'll do this. So I'll give you the GitHub repo. All right, so let's quickly go over this. So this is the GitHub repo for using SciSpacy and NLP. This is specifically looking at the COVID-19 articles. It's also called COVID-19. And this is a little bit about what an abstract would look like. So we have the abstracts of the articles, and this one's norovirus subgenomic mRNA sequence derived from, to be honest, I'm not a geneticist, so I don't know all of what these would be. And if I was asked to tag this personally, I'd be like, I don't know what I should tag them as. So that's that's where we can run it through a machine learning model that's specifically trained to actually abstract these. Just a little bit what this would look like is, let's look at the data so we know what we're processing. So this is the metadata from Kaggle COVID-19 Research Challenge. And this is the metadata file. And just to look at this same abstract, you scroll over. All right, so you have an abstract column. So this is the column that we're actually going to be processing and semantically linking all of these entities in the graph. But specifically, we want to do the pre-processing of the natural language of the abstracts themselves. So you'll see certain elements like DOI and PubMed ID and license represented when we get to the graph portion. All right, so let's go back to our repo. They have there's a link right here. You can open this and run this in Colab. So Google Colab is a Python environment. If you're familiar with the Jupyter Notebooks, it's almost exactly the same. But if you've used Google Docs or Google Sheets, this is like the Google of Jupyter Notebooks, and it allows you to do co-editing, and it allows you to do run this in the cloud. You can also use free CPU, TPU, and GPU resources to an extent. I'm not going to run this because I've pre-processed the files, but I will walk you through the different code chunks here. Excuse me. So we have installing a package. So you can see that we get SciSpacy. We're also grabbing all of the models. We're going to import those. Another thing that we use is pandas. If you've used Python before, I don't think you could ever learn Python without pandas at some point. So it's pretty predominantly used in data science and especially with Python. This one is just to do an example of a single row. So if you want to look at an abstract and run this one, you can, and this will just process the abstract for a single row using this model here that we provided. But if you're running this and you want to process all of the rows, you don't want to do that one. You'll do this, read the entire file. But one thing I do want to point out, so this is the methods that he's going to create that actually processes these tables with the DOI, which is the unique ID. We have an entity, and then we have a class. This probably doesn't make too much sense from me just talking about it here, so I'll show you an example of the output. And then this chunk right here is actually calling each of those. So taking the sample file that we provided, that metadata that we looked at, and then what we want to do is run those. So add CR. So he's calling this method here for add CR, and then take that data and then output it into a CSV. So what does that look like? It comes out to look something like this. So we have, this is the entity BC5CDR. This is one of the models from the SciSpacy. And then on the right-hand side, you can see class and you can see entity. You know, hepatitis B, hepatitis C virus. We have disease. So you could even now, just even looking at this data, you can say, okay, give me all of the articles that are pertaining to COVID, because these are all COVID-19, but give me all the articles that are pertaining to hepatitis virus or hepatitis B or hepatitis C. Or maybe we want to get into, let's see some other ones, carbon monoxide, sulfur. So if you want to look at like certain, like I'm looking at the correlations between smallpox and COVID-19. What does that look like? I'm looking for the correlations between, yeah, any of these. If I wanted to look for those individuals that have a certain precondition and want all the papers related to that precondition, this would have processed all the text with that precondition that was mentioned. And then what you could do then is derive all the papers with that precondition, maybe people with diabetes. So give me all the papers with diabetes. So that's a little bit of the output. If you ran this SciSpacy model yourself, you have the link to do that. Now let's switch back. So we have our kit, our solution that we actually created, and let's open that up. So if you click this button right here on the right-hand side, you can open a thing called Graph Studio. So Graph Studio allows you to interact with your graph database in a graphical user interface way. So you can do a lot of drag and drop. You can do data exploration, which is clicking. And you can also write your queries that you are going to derive in here. So let's do this. So the data file that you actually grabbed in the beginning or downloaded, there should be yours probably won't be called GraphGZs, but there's going to be a link called, let me show it to you quick. Oops. All right, I'm gonna run the one I have, but COVID-19 graph. So you would take this file right here, and when you're in your instance after you spun it up, you click this import an existing solution, and that's going to grab basically this whole use case that we put together, this whole workshop. It's not going to include the data. So we're going to manually insert the data or put the data on the server. The other thing it does is it has the queries, but it does not have them installed. So we're going to have to install the queries as well. All right. Just looking at chat. Are those files already inside TigerGraph, or is it pulling Google? The files are not in TigerGraph. So what we'll do is actually show you how to install the files or put the files on the server. The file mapping and everything is going to be there when this kit spins up. So we don't need to add that and remap anything. We have a question on how did you guys do in the COVID-19 challenge? We didn't enter the challenge, but we did help a lot of people either through, we have an open source initiative called Open COVID-19, and we've helped many people get started with the data and understanding how they could leverage graph with addressing the challenges, not only with the COVID-19 Kaggle challenge, but other challenges that they're having to find insights in their data. And we have another question called, can we also process those 12 gig original files to get faster results at runtime? You can process those, and you can, so get faster results at runtime. So you're maybe asking, can you return certain papers faster? Yeah. I mean, you can return papers faster if you know which papers you're looking for. I don't know if we could demonstrate a head-to-head, but finding insights in all those papers, you should be able to derive those insights at pretty much Googling speed. I always say Google speed because imagine they always put the milliseconds at the top, and they're always shooting for like 200 milliseconds or sub. You return those results as well in sub milliseconds. So I would say that's faster. All right, so let's open this. So we just imported the model. And we have the class, entities, publications, authors, journals, and license. And then we also have these things called edges. And so you have edges are the relationships between, I would say entities, but there's entities actually modeled in here, but between different things. So a thing, an author could have a publication, or he's on a publication, or that publication could have a journal or a license attached to it. So a lot of the time when you're thinking about, if you're thinking about, well, how should I model this? You really have to like look at your data, understand the data, understand what's available in your data that you're going to be ingesting. And then you also want to think about a little bit about what type of questions would I ask it? And so maybe like one of the questions would be, give me all of the journals that were published in a certain time. So maybe you want a date timestamp represented on the edge, or you could put it in the vertex, either one. The other one is maybe give me, maybe I'm interested in all the authors to a publication like this. So I'm going to separate authors, and I can find a certain author, and I can find all the publications that he or she wrote, and you can do that.
Hey, John, can you scroll up just a little bit? You can't see the bottom of that, of the schema.
Oh, interesting.
Nice.
Must be cut off on the, okay. Yeah, so let me load some data while I'm gonna leave this and I'll keep explaining. So one thing, because we spun this up, I'll try to move this up, but it'll cut off the top. One thing, we have all the data mapped and all the data elements, but the data for this use case does not reside on the server. So one thing we're actually gonna have to do is add that data to the server. And how you do that is you click on this tab, map data to graph, and we want to click on add data file. So click on add data file, click on upload file to server. And these, if you downloaded that file, this should be under, I think it's called data folder. And we're just going to do this in the background. So it's going to be uploading. And let me just open this in a new tab while this is going. All right, we'll go back to design schema. All right, so if you, and I'll drag this up. There we go. So if this was your database and you're just looking at the columns and your rows or wherever your data is, and what you're trying to do is figure out how you want to represent your data in your graph database, and you want to get started, and you're going to first click on this add vertex type. So let's create a social network quickly on top of this, and we'll just delete it. Let's say I have a person or a user. Let's say user. As user, one thing you can do, so you add a vertex. So we're going to have a user. You can add a user has a first name. And so you have these attributes. You can add attributes about the vertex. You also want to add the type of this, and this is going to be string. So the first name is a string, and let's do last name. All right, a string. All right, click add, and then we'll also have a user can. So I click this link up here called add edge type. So if we're creating a social network, a user might connect or follow another user. So let's say a user follows. So user follows. We're going to use directed because just because I follow somebody else doesn't mean they're always going to follow me back. So I'm going to add a logical direction to which way John follows Sam, but Sam might not follow John. So we can also add an attribute. Let's do follows date and date time. All right, so this would be like the most simple version of a schema for a user with the first name and last name and a follows relationship. So this is a mini social network. But I just wanted to quickly show you how the add vertex and add edge work, and how you can add the different data fields to your schema. So I'm just going to hit delete, and then let's check on our. All right, so I'm just going to add these in the background. And if you're following along, click the plus data button and just add these to the server. You don't need to click this add button because we just want to add the files to the server for this workshop. All right. All right, so this is a little bit about design schema. This is how we modeled it. We can look into the one that we modeled. So an author has an author's name. An author has a publication. So this is the paper that they published. The DOI is the unique ID for the publication. We also have the title, an abstract, and URL. This URL is actually how we would store it in a enterprise edition. You don't want to store all the data in the graph. A good analogy or a good representation of this would be, imagine you took a photo. And the photo, it has the metadata. It has when you took it, where you took it, who took it. But you would store all that information in the graph, but you wouldn't store the photo in the graph. It just doesn't make sense. But what if you took the photo and you threw it through a machine learning model, and it derived that the photo has a dog in it, it has grass, and it has some other things in it. You would store that that data in the graph as well. But again, you wouldn't store the photo in the graph. Just like we're not going to store the whole document in the graph, we're going to store the pub URL, and that's the URL to the location where that document actually resides. So what we can do is return the location of that, and then of course, if you have your database, or not database, if you have your application, you can have your application actually programmed to open that URL and have that. Oops. All right, so let's keep adding some of these files. Sample entity. So we're just adding. So the one file I showed you has the process entities and classes. These are the other models that we ran. Bio NLP 13CG is another model. So it has some more entities and classes. What we're just doing is uploading all those. All right, so I'm going to go back. And it'll ask you if you move your schema or redesign it, it's going to ask you to save. One thing you should do is save or publish your schema after you edit it or change things. You'd want to click this button before you move on. I'm going to be fine for that. Next, we want to go to map data to graph. And let me update this one. All right. So just continue to add your files. All right, so map data to graph. This is representing how the data is loaded into the graph. So if you're new to graph databases, one thing that happens when you put data into the graph is it's all pre-joined. So as the data streams in, if you're using your data lake or a Kafka or Confluent or any kind of streaming methods, if you're using a loading job and loading things, if you're using JSON or whatever the method is, and you're putting data and pushing data towards the graph, you're going to need this thing called a loading job or a method to actually tell the database on how the data should be inserted into the graph or upserted into the graph. So behind the scenes, what this is actually doing is creating a loading job. But for our use cases, it's as simple as doing a click. So when you added the file to this, one thing, if you did click the add button after you edit all your files in here, Let me just show you quickly how to do this. So you would, if you're doing it from scratch and not following along with this workshop, but just doing this on your own, what you would do is you would add your file here. You would then notice that, okay, this one actually has headers. So we're going to click has headers. And this file does not have enclosing characters. Everything looks good here. So we click add. If you're following this workshop, we just need to add the files to the server. All of this, the data has been mapped, so you don't need to click add. So let me add the next one. All right. So if you're doing this from scratch and you just clicked add, you would see a file like this appear. For this workshop, we're going everything's sort of been added and pre-mapped. But if you were doing this for the first time, you would click on the file and then you would click on this map data to vertex, and then it would create this line here. And there wouldn't be any arrows here. You would want to create those arrows. So you'd click on the sample data, and then click on the ID or wherever the data is being pushed to. So in this case, this is the entities that were extracted. We can see nortavirus is one entity and it comes into a class of simple chemicals. That might fall under other classes with these other models. We don't know. But we know that class is going to have a class ID, and we also want that class to have an attribute. So we have class type. So we do the same thing for all of these, and we map them all. And you can just see, click and drag, or click, and then it creates this relationship. And we're almost done with the files here. So which one do we have? Craft. So this is pretty impressive that we're able to do this all within this hour. We're going to be able to take process text. We're going to be able to semantically link it. And you can relate that text to how it would be upserted into the graph. We're going to load the data, and then we're going to run a query on it. So as soon as these files are uploaded, the next portion of this is that we're going to actually load this data. So to load the data, you click on this Load Data tab. And this is being utilized through the Graph Studio. All of this can also be written through GSQL scripts. And I can show a little bit about what those look like. All right, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I think we're good. So we'll cancel. All the data has been loaded. So let's moment of truth. And we'll click play, click continue. So now what it's doing is it's taking all the files that we have on the server. It's taking the mappings that we gave it. And then what it's going to be doing is loading that data into either the vertex, or if it's from a primary ID to primary ID, it's going to create a relationship for that. And so we can see it here loading in real time. We have a total vertex of 325, 455. Let's see how high it goes here. You can see that the files are loading here with the percentage signs. We're at 1.5 million relationships. Now that we have our data loaded, you can see again on the right-hand side, 1,792,000 edges, and we have 576,000 vertices. So the next thing we want to do after this data has been loaded is that we want to go to Explore Graph. So typically when you land on this page, you'll have the search vertices on the top left here. You have expand from vertices. You have some built-in paths algorithms. You have the find connections and run queries. So what you can do here is actually just explore your graph. And if you know vertex types and the vertex IDs, you can input those here. And if you had a specific one that you wanted to search for instance, if you had an author and you knew the author's name, you could put that in here, or the author ID, you could put that in here. For me, I don't know any off the top of my head. So I'm going to choose just a single author. So you could choose I think by default it's got 5 authors, or 5 of every entity. And then if you want to choose a specific one and return a specific number, you can do that by just electing how many you'd like to return, and then also electing which vertex types you would like to return. So let's do author. All right, so we have one author, and we have the data about the author. Now let's look at what publications maybe that this author has. So one way we can do that is by just double clicking, but sometimes we don't know how much data is actually connected to this this person. So what I'm going to just do is do the expand from vertices, and then I'm going to elect to go towards publications. So I just want to choose publications. These are by default selected all, so you just unselect all of them and then choose the edge that, or towards the edge that you want to go towards. Now you can get specific and elect not to have all, but for our case, because I already know that there's only one edge, you can just leave it as all. Or if you want to be specific, you can choose pub has author. So in our case, we can be specific. That's fine. So then, wow. So this author has a lot of publications, and you can elect how many that you'd like to return for. In our case, we have 50. So if we can return up to 50. If you want to add more, you can add more. But let's look at this data here a little bit. So we have the publications, we have the titles of the publications, the IDs of all the publications. In most cases, though, there's multiple authors on a publication. So I'm just going to select a couple more. And what we'll do is actually let's go towards other authors. So what we're going to just do is look at, based off these ones selected, how many other authors are there related to that. And this looks a little messy. It's a little hard to see any patterns or see any connections. So one thing you might want to do is change the layout. So if you click on change layout, you can choose between these different options. We're going to just choose force. And you could start to see things emerge a little bit. For instance, these publications right here, looks like there's a little group of authors that are co-creating. For instance, this author and this author co-created on 2 different articles, and these 2, 3, 4 have co-created before. So if we want to maybe even dive into those and look at publications, so we can go back. We're going to go back and forth just to explore. So we're going to go. Let's go towards publication. All right, let's see if they have other ones that are from the same authors, and let's make this look a little bit better. All right, so just looking at this, we can see some connections. I guess it's a little tough to see all the authors that they co-created together, but we can definitely see that there's groups of authors that are co-creating with one another on specific blogs. So those blogs we don't, or those publications, we don't know exactly what they're co-creating on. Maybe they're all in the same department or same university or same group, and they are specializing in a specific topic, maybe a respiratory diseases and COVID-19. And because they all work together, they have co-authored many articles or publications before. So this is just a short intro to Explore Graph. It's just a good way to look at data, and maybe because I found it interesting when I looked at this and saw this pattern of multiple authors connected to publications, maybe I want to write a query that would actually derive these clusters of individuals that have worked together and published together. And that might be of some interest. And maybe look at the entities that are related to those communities of clusters of groups. So that off the top of my head, just looking at this data, that would be of interest maybe to write a query about. So we talked about we talked about it would be nice to have give me all the papers related to cancer. And since we now have our entities extracted out of our publications, we can do that. What we'd want to do is start at the class of cancer. And so let's look at a query that actually does this. So these queries are installed with or they're provided with the kit. You will have to run the install button. We did that earlier. Excuse me. But after you run the install, they get compiled and get exposed as REST services. And you could see that this is totally callable now. You can we called this one class pub. So this is grabbing all the publications related to this class and given how many you'd want to return. So just taking a look at this, we're starting at class. So you have to start somewhere. And for our instance, we're going to start at class. And typically this is called a seed. So we're going to seed it, and we're going to go from the seed to entities. So we're going to basically crawl this edge right here, and we're going to go to entities. But we're not going to go look at all entities. We only want the entities that are related to the class that we provided. So we're doing a select, and we're giving a proxy value. So we're saying select the entities where the class ID equals C. So if we did put cancer, the class ID would equal cancer. So it only return the entities related to cancer. And then what we do is we assign that to ents. And then we're going to use that down here. Now you will notice that like select from, where, order by, descending limit. This is pretty SQL-ish. GSQL was built to be really familiar and enable the developer to actually quickly learn the language and be able to write in the language and derive instant value from having the language and their background in SQL. So the only thing different is that in traditional SQL, you don't have from a seed to along an edge to, you don't have from a vertex to an edge to a vertex. So that's something that's unique with graph languages. We're actually crawling the edge. So returning ents, we're going to go from ents to, we're going to crawl this next edge. So we're only going from all of the entities that were related to cancer, and we're going to crawl the edges to publications. So we're going to go from cancer, grab all the entities related to that, all the entities related to cancer, then we're going to grab all the publications related to all the entities that were derived from cancer. And we're going to do a simple logic, and we're going to just say, okay, the ones that are more interesting to me are the ones that have the most number of entities in the article that are related to cancer. You could put whatever logic you would like. This is just a super simple logic that we decided to put for this query. And then just return that. So this is what it would look like. And let's just choose 5. All right, so we got some values returned. If we want to navigate to view JSON results, this is the JSON. And of course, with this, you can do whatever you'd like with it. If you're in your web app, JSON is pretty easy to consume. If you're in your Jupyter notebook, and you take your JSON data, you return your JSON data, you can use pandas or data frames to manipulate it and be able to process it or do whichever activity you would like to do. So maybe you'd want to visualize your data, or maybe you'd want to run machine learning on your data. You could do that as well. JSON's pretty universal, so you could do anything that you would like, and it's as simple as passing some parameters and calling that REST service. The last thing I'd like to show you is the similarity algorithm. So TigerGraph has a library of algorithms that you can actually modify. Because GSQL is turning complete, you can pretty much write any algorithm that you dream of. Just dream about it, think about it, and if you can logically think through how you construct it, you can write it in GSQL. And then from there, you can actually use it. So all of the algorithms for TigerGraph are open source. They're available. You can modify them. You can change them. You can change the parameters. You can change different the different elements about the algorithm itself. And in this case, we took a off-the-shelf algorithm to do. It's using Jacquard to do similarities on the papers. Now, is Jacquard the best algorithm for this? Probably not. You could use the cosine similarity algorithm, but this is just an example of one that you can run, and this is what it looked like. Excuse me. And then why this would be important, just thinking about it, is you have, let's say you're a researcher and you just determined that I found the publication that I love. I found the publication that I was looking for, and that this is the one that I was out of all these publications has been the most interesting and relatable to what I'm in my research domain. So then let's say I want all the papers that are most similar to this paper. Well, then maybe it would be what you could do is actually take that and then run it through your similarity algorithm. So I don't know. Let's see if I can grab just any of these, because I think it's going to take a DOI. If not, all right. So we just passed a random publication. Top. Let's choose top 5. Okay, top 5. All right, so we just grabbed some random paper and found the most similar papers to that paper and returned it. Out of those 60,000 papers, what are the most similar papers with the similarity score? And just did that. We didn't have to move the data. We didn't have to do anything. We just ran it natively in the graph database. Again, this is available through your REST service. So you could actually just call this cosine similarity and return the most similar publications and do that interacting with your database without even going into Graph Studio and using this. You could just call to your REST service, pass the parameters, and get the JSON results. So with that, thank you for being here. All of the material will be provided through either the description link in YouTube or in the chat or through an email. With that, thank you so much and have a good day.